Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Text: The Cosmic Symphony's Accelerando unveiling. The universe's expansion. The year 2011 marked a momentous occasion in the annals of cosmology. The Nobel Prize in Physics was jointly awarded to Saul Perlmutter, Brian P. Schmidt, and Adam G. Riess for their groundbreaking discovery, the accelerating expansion of the universe, a phenomenon unveiled through meticulous observations of distant supernova. This essay delves into the intricacies of this remarkable achievement, tracing its intellectual lineage, dissecting its core tenets, and assessing its enduring impact on our understanding of the cosmos. The intellectual groundwork for this revelation was laid during the late 20th century. Prior to the supernova observations, the prevailing cosmological model leaned towards a decelerating expansion, governed by the gravitational pull of matter. This paradigm drew support from the Big Bang theory, itself a radical departure from the static universe envisioned by many earlier scientists. Key figures like Georges Lemaitre laid the framework for an expanding universe, and Edwin Hubble's observations of redshift in the spectra of distant galaxies provided initial empirical evidence for this expansion. These pieces of the puzzle, however, revealed only the existence of expansion itself, providing no insight into the rate of this expansion or the forces driving. The quest to determine the fate of the universe pushed research teams to study supernova, particularly those classified as Type Ia. These stellar explosions, the thermonuclear detonations of white dwarf stars that have reached a critical mass, served as standard candles. This meant they exhibit roughly the same intrinsic brightness, allowing astronomers to determine their distance based on their apparent brightness, as seen from Earth. The critical advantage of Type Ia supernova was the enormous amount of energy released, making them detectable across vast interstellar distances. The challenge, therefore, lay in precisely measuring these faint beacons within the colossal expanse of the cosmos. Perlmutter, leading the Supernova Cosmology Project, and Schmidt, heading the HIGH Supernova Search Team, embarked on independent, yet ultimately converging, research journeys. Both groups faced significant hurdles, which included securing access to powerful telescopes, developing sophisticated data analysis techniques, and painstakingly identifying and observing these rare cosmic events. The task required overcoming the considerable challenges of astronomical observation, including the accurate removal of atmospheric distortion and the precise measurement of spectroscopic redshift to determine the distance and velocity of these supernova. The mechanism of these Type Ia supernova is itself profoundly interesting. A white dwarf star, the compact remnant of a sun-like star, accretes matter from a companion star, gradually increasing its mass. When a white dwarf reaches the Chandrasekhar limit, approximately 1.4 solar masses, it becomes unstable and undergoes a thermonuclear runaway. The star's core ignites with explosive fury, releasing an enormous amount of energy in a process. It is remarkably homogeneous. The brightness of the explosion allows astronomers to gauge its distance, and the observed redshift of the light emitted reveals its recession velocity. The essence of the discovery lay in a deviation from expected behavior. Based on conventional models in 1998, scientists anticipated that the expansion of the universe, driven by the gravitational attraction of matter, would be slowing down. When analyzing the data from numerous Type Ia supernova, both teams noticed that the distant supernova appeared fainter than expected. This indicated they were further away than anticipated, implying that the expansion of the universe had been accelerating over. This observation represented a radical departure from the prevailing scientific consensus. To account for the observed acceleration, cosmologists proposed the existence of dark energy, an enigmatic force that counteracts gravity and permeates the fabric of space-time. Precisely what constitutes dark energy remains one of the most significant unsolved problems in modern physics. The simplest explanation is the cosmological constant, representing a constant energy density inherent to space itself. However, alternative possibilities exist, including dynamic forms of dark energy whose density changes over time, or modifications to the theory of general relativity. The discovery spurred numerous theoretical advancements and experimental programs aimed at gaining a deeper understanding of its nature. The immediate impact of the discovery was profound. It reshaped our understanding of the universe's composition, indicating that dark energy accounts for roughly 68% of its total energy density, with dark matter comprising approximately 27%. And ordinary matter constituting the remaining 5%. This new cosmic inventory fundamentally altered our perceptions of the universe's long-term evolution. It suggests that the universe will continue to expand indefinitely, ultimately leading to a heat death, where all energy is dispersed and all structures break down. The implications extended far beyond cosmology. Fueling cross-disciplinary investigations, the discovery spurred intense interest in fundamental physics, especially in the realm of quantum gravity and string theory, as researchers sought a theoretical framework for dark energy. The finding also resonated within mathematics and data analysis as teams sought to improve the statistical tools required to analyze large data sets with precision, a task which is still ongoing. The immediate aftermath saw intense scrutiny of the team's methodologies. Critics challenged the assumptions made in determining the distances to the supernova, the accuracy of the calibration methods, and the potential for systematic errors affecting the data. The teams responded with meticulous work, refining their techniques and addressing these specific concerns. The robustness of the findings was further confirmed by independent observations using different methods, such as the cosmic microwave background radiation and the baryon acoustic oscillations. The influence of the work on future research has been extensive. The discovery fostered a new era of observational cosmology, driving the development of advanced telescopes and advanced surveys, such as the Sloan Digital Sky Survey and the Dark Energy Survey. These projects have aimed to map the distribution of dark matter and dark energy with unprecedented accuracy. More recently, the James Webb Space Telescope promises to reveal even more detailed insights. Such subsequent investigations built upon and further validated the initial findings, solidifying their position as a cornerstone of modern cosmology. The discovery also directly influenced several individuals who would make significant contributions to related fields. For instance, the work on the statistical techniques developed to analyze the supernova data influenced the careers of multiple statisticians. Furthermore, the discovery acted as a touchstone for younger physicists. The discovery was a testament to the power of careful observation, rigorous analysis, a collaborative spirit of scientific and, in conclusion, the 2011 Nobel Prize-winning discovery of the accelerating expansion of the universe, realized through observations of distant supernova, marks a defining moment in the history of cosmology. This accomplishment, driven by the diligent work of Perlmutter, Schmidt, and Riess, revolutionized our view of the universe, unveiling the presence of dark energy, a mysterious force accelerating the expansion of space itself. The work's legacy extends beyond the field of astronomy, influencing theoretical physics, statistical modeling, and future research. The cosmic symphony continues to play, unveiling more of its secrets with each new observation, and these scientists helped to reveal a crucial and previously hidden element of that music.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.